Today we're going to start ionic compounds and metallic bonding, which is Unit 4. We're going to start easy and talk about what a chemical formula is. A chemical formula is going to show you what elements are in a compound. It is also going to tell you how many of each element is in that compound using subscripts. The following shows you some examples of chemical compounds written as a chemical formula. This first one we have is sodium chloride. Notice how we have sodium, Na, and chlorine, Cl. This is an example of a chemical formula. There are no subscripts written here to indicate that we have one of each atom. If we look at carbon dioxide here, CO2, we have carbon and we have oxygen, and then there's a subscript 2. This subscript 2 indicates that we have 2 oxygen atoms. Next we have magnesium chloride. Here we have magnesium, and then we have chlorine. Again, this little subscript 2 indicates that we have 2 chlorine atoms. For this last example, there's sodium, and we have phosphorus. Here we have this 3. This 3 indicates that we have 3 sodium atoms. Sometimes we are going to have chemical formulas with larger groups of atoms. These larger groups of atoms you will see over and over and over again. These are what we call polyatomic ions. If we break down this word, polyatomic ion, it gives us a clue as to what a polyatomic ion is. Poly is a prefix that means multiple. Here we have atomic, which is referring to atoms. And then we have the word ion. An ion is any atom with a charge. So if we have a polyatomic ion, we have many atoms with a charge. Some examples of polyatomic ions are as follows. Here we have OH with a negative charge, PO4 with a negative 3 charge, NO3 with a negative 1 charge, and NH4 with a positive charge. There is a list of these polyatomic ions that can be found in your reference table on page 7. These chemical formulas are different than what we saw previously because of the indicated charges. This ion has a name, and it is hydroxide. Hydroxide consists of 1 oxygen atom and 1 hydrogen atom, and then we have this negative 1 charge. Notice how there's no number written, because normally in chemistry we do not use ones, or we don't write ones. If we're going to write it, we're going to assume that it's there. Here we have phosphate, the phosphate ion, where we have 1 phosphorus and 4 oxygen atoms. Here we have a negative 3 at the top to indicate phosphate's charge. Now this negative 3 indicates that we have 3 extra electrons. So this negative symbol here can also mean electron. Here we have nitrate, and it's NO3 with a negative 1 charge. Then we have this ion here named ammonium, where we have 1 nitrogen and 4 hydrogens. And this one now has a positive charge. This is what we call a cation. Cations have a positive charge. This is the only polyatomic ion on your list of ions that has a positive charge. So like I said, these are in your reference tables on page 7. You are not expected to memorize these ions. You are expected to be able to recognize that you have them in your chemical formula. If we have more than 1 polyatomic ion in a chemical formula, the group will be written inside of parentheses. Okay? After you have the parentheses, there will be a subscript on the lower end of the right parenthesis that will let you know how many ions there are in that chemical formula. For example, let's say we had NaOH OH. Okay, so like I said, you're not expected to memorize what OH is, but you have to be able to recognize that OH is a polyatomic ion within your chemical formula. So this is an example of where we only have one polyatomic ion, and it is hydroxide. So here we have sodium hydroxide. Another example would be if we had this. Excuse my handwriting on this. Here we have beryllium hydroxide, and as you can see, the parentheses indicate that we have two hydroxide ions. So if you see parentheses, that means you have more than one polyatomic ion group here. Alright, so we're going to kind of move on and talk about electron configuration. We talked about electron configuration in Unit 3, when we talked about S, P, D, and F block elements. So we're going to kind of elaborate a little bit more on that and focus particularly on valence electrons. Your valence electrons are probably some of the most important electrons solely because they are the only electrons involved in chemical bonding. This whole unit is on chemical bonding, so we're going to spend a lot of time talking about valence electrons. But your valence electrons are in the highest energy level, and we can use electron dot diagrams to show the number of valence electrons an atom has. Electron dot diagrams are very similar to the Bohr model. However, we are not going to draw the entire atom as we did in the Bohr model. Here, we're only going to write the symbol of the element, and then we're going to use large dots to represent each valence electron that element has. Just like in electron configuration, we have to put one dot on each side of the atom before we can start doubling them up. So if we wanted to draw an electron dot diagram for the following, here's strontium. Strontium is in group 2. Since strontium is in group 2, it will have two valence electrons. So here you have strontium, the symbol is already written. And if I want to make an electron dot diagram, I'll put one electron here and one electron here to represent the electron dot diagram for strontium. Next we have silicon. Silicon is in group 14. Since it is in group 14, it will have 4 valence electrons. And you draw them, one on each side of silicon. Before you can pair them up, silicon only has 4, so you draw one on each side. Next, we have chlorine. Chlorine is in group 17, therefore it has 7 valence electrons. You put one electron on each side of the symbol. So there's 1, 2, 3, 4, before you can double them up. 5, 6, and 7. And there's chlorine. The cool thing about your electron dot diagrams is that, say for example we're looking at strontium. Strontium is in group 2. That means all of the elements in group 2 will also have a very similar electron dot diagram. So let's say we have magnesium. Okay, magnesium is in group 2, therefore its electron dot diagram will look very similar to strontium, except the symbol has changed. Same thing for silicon. It's in group 14, so is carbon. So since they are in the same group, they share similar properties. And one of the similar properties that they share are their number of valence electrons. And if we had fluorine, fluorine is in group 17, so it will have a similar dot diagram to chlorine in that it will have 7 valence electrons. And we draw one electron on each side of the symbol before we double them up, like so. Okay, So those are your electron dot diagrams. As I was saying before, your electron dot diagrams are going to have similarities depending on their group. And here we can see group 1. We have hydrogen, lithium, sodium, and potassium. They all have 1 valence electron. If we look at group 15, they have 5 valence electrons, so all of their electron dot diagrams look the same. So how are these elements forming a chemical bond? Well, the first thing we need to know is that all atoms, for the most part, are going to follow the octet rule. The octet rule states that atoms are the most stable with 8 valence electrons. And there's only one group on the periodic table with 8 valence electrons, and that is group 18, the noble gases. Okay? So you essentially want to have the same electron configuration as a noble gas. So we have Ns2 and Np6. Remember, this is electron configuration where N is energy level, S is subblock or sublevel, and then the 2 tells you how many electrons there are. If you add these two numbers together, you get 8, and that's how the noble gases work. So this octet rule only applies to the S and P block elements. So the S block are groups 1 and 2, and the P block are groups 13 through 18. Okay, notice how we are not talking about the transition metals yet. We will talk about them separately. Okay, so the transition metals are different. They follow their own rules. So in order to get 8 valence electrons, atoms will react in a couple of different ways. They will either transfer their electrons, meaning that one will lose an electron to drop down an energy level, and the other will gain electrons until they have 8. The atoms that lose electrons are your metals. The ones that will gain electrons are your nonmetals. And you can tell what a metal and a nonmetal is based on where they are located on the periodic table. Remember that the stair-step line separates your metals and your nonmetals. The other way that atoms can get 8 valence electrons is if they share their electrons, so everyone has 8. This will only occur if they are the same types of metals, or same types of elements, For example, metals will share with metals, and nonmetals will share with nonmetals. However, a metal will not share with a nonmetal. They're going to transfer. So again, metals share with metals, and nonmetals share with other nonmetals. Okay, they will not share with each other if they are two different types of elements, which leads us into our next slide here, which talks about the different types of chemical bonds. Chemical bond is the force that holds two atoms together, and we have 3 different types. We have an ionic, covalent, and metallic bond. An ionic bond is going to be between a metal and a nonmetal, where they are going to transfer electrons. The metal will give to the nonmetal. A covalent is between 2 nonmetals, so nonmetals only, and they share. And metallic bond is between metals only, and they will share their valence electrons. So, one last time, ionic, metal, and nonmetal, where the metal will give its valence electrons to the nonmetal. In a covalent bond, you have 2 nonmetals, and they will share with each other because they are similar atoms. And then we have a metallic bond, which is metals only, and they will also share their electrons to create what we call a sea of electrons.